Thank you for the welcome, and thank you, Rob. Systems engineering is the discipline of looking across the problem, listening to the customer, and giving the designer a plan that the designer can work to in order to make sure that all the customer's needs are being met. The larger the system is, or system of systems, I think the more important it is to do a broad collection of these requirements and a broad analysis of what their interactions are. We'll talk about what this picture is on the cover slide later. There are three things that I'm hoping that everyone takes from this short talk. The first one is that asteroid mining is a very complex system of systems. The economics, which is the question you always get from the media, we're going to be determined by how well you do prospecting as opposed to how efficiently you do transportation as opposed to how well you do the actual extraction and that sort of thing. So these interplays are what are going to determine the economics, and we have to understand the mathematical and quantitative relationships between those subsystems of the large system. So the rest of this talk will be a detailed mathematical note. I wouldn't do that. The second thing I'd like you to really take away is that robotics is the key to the whole thing. I still do get questions from the media about, well, when these astronauts are walking around in the asteroids, no. One thing that the International Space Station has taught us is that long habitation in space is bad for your body. Radiation damage increases your risk of cancer. The zero gravity environment increases the bone mass loss from your bones. Commander Peggy Whitson, who was one of the mission commanders, managed to keep her bone mass loss down to only 1% by working out 5 hours a day. So this is not a place for human beings. Robots are going to do prospecting, robots are going to do extraction, robots are going to do transportation. And there are challenges to these robotic missions that are yet to be solved. I hope that students realize that this is absolutely fascinating for a career. You can get into working in space robotics, it's only going to get bigger. And it's not just about mining, there's a lot more that space robotics are going to be called on to do. Which brings me to the point about technology sharing. A lot of these robotics technologies that you might use for mining are in common with technologies that you might use for servicing, robotic servicing of spacecraft in Earth orbit, to extend their lives, to repair them, to reuse some of their hardware. And missions like protecting the planet. So the Chelyabinsk meteor strike is an example of why we really need to pay attention to that. I mean, that was far too small to see with our current set of asteroid hunting telescopes, and it injured 1,000 people. So, and the technologies that we might want to use to transport mined materials from asteroids probably have a lot in common with technology we might want to use to deflect an asteroid to keep it from wiping out civilization on Earth. So I don't know anything about mining, so I went to the museum at Newcastle, to the BHP wing, and I came across this 1930s era coal saw. This is an amazing device. It saws the coal out of the seam, and then there are things that shuttle the coal back and load them on a car, all in one sort of smooth operation. This is a 100-ton drag line. A crane doesn't weigh 100 tons. Each bucketful weighs 100 tons. So I just showed these pictures to say that whatever our preconceived notions are about mining, they're going to be wrong when it comes to mining asteroids. A 1970s era view of what systems engineering is these 4 steps. Define the functions that must be performed, and that cannot be done without a dialogue with the customer. So this is not an engineer-only function. And then quantify those functions. How well do they have to be performed? Those are called requirements. Then the system engineer investigates alternatives for satisfying the requirements. And finally, the system engineer defines tests by which and this is not tests like, well, I'm going to do a shock and vibe test on the satellite. These are tests that the designer can use to make sure that the proposed design, his or her proposed design, meets the requirements demanded by the customer. So these four functions at a very high level are what systems engineering is. And it's never done. It's not that you do this at the beginning and you walk away and you're done. You're always re-interacting with the design team and with the customer to make sure that the requirements deck is continually updated. We're not able to talk about all four of these today. We're going to talk about the functions of mining and some of the alternatives. And that's all. So here's my ignorant functional breakdown of mining. Prospecting, I learned last night from a real prospector who's here, has at least 3 phases and how that's done. Then we have to survey and prepare and excavate and process. That's actual real sort of mining. Finally, we have to transport this stuff somewhere else. And we'll talk about only the first and the last of these functions. We'll talk about prospecting from a space engineer's point of view, not from a real prospector's point of view. And we'll talk about transporting from a space engineer's point of view. So before last night, this is my understanding of prospecting. And then last night I met a real prospector, and I got to understand what that's really all about. It's a highly technical field. It involves physics and chemistry and using the latest remote sensing technologies and that sort of thing. Still, this is a useful image. And then in terms of transporting, we have some short-range transporting that goes on, and that's to get it to the medium-range transporting stuff, and finally to the long-range transporting stuff. When I was up at Newcastle, I got that picture, and I noticed that every one of those coal carriers had, the name was in Chinese. And for the purposes of this half-hour discussion, we're only going to talk about long-range transport, so not short and medium range, but how we get the stuff to where we're going to use it. And as Andrew mentioned, robotic prospecting is already happening. I mean, this is a vehicle that scouted out a likely place to do some drilling, took out its little brush and swept it off, and then drilled a hole. And I was in discussion with the inventor and the builder of this arm and assembly yesterday, who told me that we're trying to make measurements of the chemistry in here to parts per billion. So a big issue here is cleanliness and sample non-contamination. We're so privileged to have Renee Frede here to talk to us at this conference and then to give a general public lecture tomorrow night. So we'll understand in more detail how this does prospecting. There's other kind of prospecting going on as well. Notice that the first product that both of these new companies are putting out are telescopes in space. Doesn't that look like an impressive object? That's how big it is. And the reason is to keep its cost down, so they can put lots and lots of them out there. And Deep Space Industries is doing the same kind of thing. I'm a little less familiar with their technology, but these are small, inexpensive telescopes that are going to be put out using rides of opportunity on launch vehicles in order to find candidates to mine. Now, we can also do this sort of thing using existing systems that are out there for other purposes. So this is the much larger, much more expensive WISE spacecraft from NASA, which has helped to find a lot of new asteroids itself. So prospecting, you can take advantage of data of opportunity as well as dedicated systems. Here's another kind of prospecting that we've done. This is the Grail mission. These are 2 satellites in a leader-follower configuration going around the moon. And because of their very precise ability to do relative position keeping, they can actually measure gravitational inhomogeneities on the moon. So you can find lumps of stuff under the surface that you didn't know were there. That's another kind of prospect. Does that have applicability on asteroids? I don't know. One thing I do know is that since asteroids are so small, the orbital velocities are very low. So this would be a very, very stately event going on around an asteroid. Nevertheless, gravitational prospecting, I mean, we do gravitational measurements here on Earth to find oil deposits. So this is the equivalent of that in space. And now I get to explain this diagram. Eventually, you've got to land on an asteroid and find out what's inside of it. One of the problems with asteroids is they don't have a lot of gravity. So Curiosity, for example, would be unsuitable to operate in an asteroid, because once it pushed that drill down, it would just go floating off into space. So you have to maintain some kind of continuous grip on the asteroid in order to do your sampling, to do your drilling. This particular device was a proposal to NASA's Innovative Advanced Concepts program using a reconfigurable robot. So these are sets of identical modules that can reconfigure into different shapes and different branchings and that sort of thing. Because the idea was, we don't know a priori what size of thing we'll have to grab when we go to an asteroid. So this would enable grabbing a wide range of objects in order to maintain that grip and do the sampling and drilling, whatever else needed to be done. The full system concept is that this object is actually lowered down to the planet by this lander, and then the lander pulls itself down on a cable, and then this object helps the lander to anchor itself before it goes wandering off to do its prospect. NASA wasn't really excited about that, but okay. I think we have to think in innovative terms about how we're going to work on very low gravity bodies. If you try to do this by continuously thrusting with your propulsion system to maintain position on the asteroid, you're going to find out that your missions are very short. So this has the advantage of not requiring continuous consumption of propellant. But this is clearly one of the technical challenges that have to be addressed, and we need to include that in the sort of systems engineering deck right at the beginning. Not a lot of gravity. How do we react against an object without floating off into space? Where are asteroids? So we're going back to some things you learned in high school and some things you didn't. So we probably did learn about the main asteroid belt. The orbits here are, the blue is Earth. So Venus and Mercury are not shown on this diagram. And then this is Mars here. This is the main asteroid belt. And then this is Jupiter's orbit. And something you may not have learned in high school is that there's a group of asteroids preceding Jupiter in its orbit and another group following it. Those are called Trojans. Every now and then one of them gets knocked out of place. These are unstable orbits, actually, so they'll come ripping through here. Some of these are pretty big. As a matter of fact, the only reason we know that they exist is because some of them are big enough to be seen. There's also a number of asteroids that are actually nearly co-orbital with the Earth and nearly co-orbital with Mars. If you've heard of the Apophis asteroid, the one that's going to do a close approach to Earth in 2029 with the possibility of impact in 2036, that's Apophis is nearly co-orbital with Earth. And so let's take a look at a mission to Apophis that a Brazilian group did a study of. How would we go and visit Apophis from Earth? So we have Earth's orbit in blue, Apophis in red, and then the dotted line is the spacecraft leaving Earth's orbit and then catching up with Apophis and going to visit it. That's a reasonable sort of paradigm for a mining mission. With a pretty good high technology thruster, that took 435 days to get there. So the time scales that we think about for space mining are a little bit different than they are for terrestrial mining. With a really, really good innovative thruster, less than a year, these are days, less than a year was required to get to Apophis. But notice also that of whatever you launch, it took 20% of the mass just to get there, 20% of the mass and fuel just to get from Earth to Apophis. The take-home message from that is that the fraction of mass that you get to bring back with you in a space mining mission is much smaller than you put in one of those ore loaders that you saw on the previous picture.
Well, is this assuming ion thrusters?
Yes, this is a pulse plasma system, and this is a Hall thruster. Should have mentioned that. So, and of course, the story's a lot worse with chemical. Unless, well, we'll talk about that later. Okay, so I get it. All right. There are alternatives. There are ways to save some mass, some propulsion by doing things like slingshot. So this was the Stardust mission, which was launched in the late 90s and did an encounter with Comet Wild 2 in 2004, I think it was. And it saved some propulsion by doing a slingshot maneuver. So the original launch put Stardust into this elliptical orbit. This is the Earth's orbit here. So we've broken away from the Earth, and we're now in an orbit around the sun that's elliptical. And as we come around here, we position very carefully to get right next to the Earth so that it pulls us along, and it makes the ellipse considerably larger, like it did here. So rather than having to use a rocket to increase our aphesion point, we used the slingshot maneuver from the Earth that added about 2 kilometers a second to the orbital velocity. And then on the third loop, they did not do a second gravity assist. This is just the third loop coming around. By this time, the comet has come around, and there's an encounter 5 years after launch. So one of the things about using slingshots is there's a timing issue, and there's a time. So you're basically trading time for fuel. How does that work with the economics? I don't think anybody has an idea. Speaking of fuel, though, there are some sources of it out there. This is from a paper by Skoudas and Lavoie, 2010. This is the North Pole of the Moon, and these are craters where we know that there's ice, water ice in these craters. If we went up to mine that fuel, that may be an economic product. Never mind platinum, never mind rare earth metals or whatever. This has economic value in the right kind of architecture. And it also could be used to enable the mining architecture itself. You could create a fuel depot in space that helps solve the problem that I was pointing out in the previous couple of slides about how much propellant you have to consume just to get to the asteroid. And you'll have to consume an additional amount to bring it back. But of course, this adds complexity to the whole picture. Okay, we were just thinking about going to an asteroid and coming back. Now we're thinking about going to the asteroid with something else, going to the moon, and they're getting some fuel, and they're coming over here, and we're refueling, and how do we do that? We have a design. So it makes the picture even more complex. Which brings me to artificial intelligence. I spent several months working on a project at the University of Southern California to develop an artificial intelligence tool for searching design spaces, for looking for optimal solutions where there are trillions of possible combinations of components and of mission parameters and that sort of thing. It seems simple. I'm not the inventor of this system. Dr. Tatiana Kishkailo, once the Russian champion in their computer programming competition, it was the inventor of the system. I was the space guy on this team. What you have to do is you have to figure out what all the engineering rules are. How much does this amount of propellant change the orbit? How does the slingshot maneuver work? How much stuff do I want to bring back? Am I going to re-enter it in the Earth's atmosphere? Am I going to use it in space? Those are engineering rules, and then there's a database of the components. This is a lot of work to assemble all that data. But once you've assembled it, you just keep using it over and over again. Each time you run the system, you can say, what do I want to optimize against? And this is always a question for the systems engineer. What is my optimization metric? Is it fastest time, lowest cost, some combination of those? And there are many, many other possible optimization metrics. What are my mission requirements for the specific mission? But this system, using the same kind of logic that you use to play Sudoku or to play, this happens to be Ken-Ken, which is a variant of Sudoku. Using that same kind of logic, this can very quickly find optima in these enormous trade spaces. Artificial intelligence, done properly, is it's an overused term, it's a misunderstood term, but it really means using computers for their best advantage. And this kind of system is probably essential for thinking through the choices that have to be made to design a satisfactory asteroid mining system. I think it goes without saying. I mentioned how important I think robots are. These are some robot missions you may or may not be familiar with. I'll mention what they are. This is a historical mission. This was completed successfully in 2007. It's called Orbital Express. It proved that one spacecraft could refuel another spacecraft, could change the spacecraft's battery, could change the spacecraft's flight processor successfully on orbit with no human interaction. All done completely autonomously. This mission was flown in 2007 with 100% success. A mission that is going on at this moment on the International Space Station is called the Robotic Refueling Mission. This is using human-operated robots now, not autonomous. This is an autonomous demonstration, but to do some of the operations you would need to do to refuel satellites in geosynchronous orbit that weren't designed to be refueled. So you got to go up there and cut wires and take insulation blankets off and unscrew caps and that sort of thing using robots. Those tests are being done on ISS right now. This is a project at DARPA that won't fly for several years, but it's to go and harvest space junk and reuse some of the valuable things like the large antennas in geosynchronous orbit, pulling them out of disposed satellites. And finally, the very long term, people talk about space solar power. This is one person's diagram of the space solar power installation, but this is huge. This is a kilometer. These are thousands of square meter objects. We need robots to build something like that. The assembly and construction of this has to be done by robots. Professor Koshnevis, who introduced me, is the inventor of the contour crafting technology, as I mentioned. Here is a proposal of his to NASA to use lunar regolith to do contour crafting structures on the moon. As Andrew mentioned, the timing of this is very fortuitous. This object was undetectable with all current sensors, and yet it injured 1,000 people. That's to be kept in mind. Many of you know, I think, what Barringer Crater is in Arizona. This is a picture of it. The object that created this crater only 49,000 years ago. I mean, human life and the beginnings of human civilization were already on the planet. This object was 30 to 50 meters across. Marginal weather, any of our systems today could have detected that. The crater is 1.6 kilometers across, so compare that to, say, the CBD of Sydney or your favorite city, and you'll see that this is a significant event, and one that one might wish to prevent. Did I say that that's 1.6 kilometers across? Now, the WISE mission, one that I showed you the picture of the spacecraft earlier, was given a second mission after its initial infrared survey of the deep sky was completed, and that mission was called NeoEyes. And it was looking for potentially hazardous asteroids. Now, potentially hazardous asteroid was defined in the survey. Is that me? Oh, okay, great. You're going to stop that. I have 2.5. As an object that's 150 meters or more in diameter, and of course it's Earth orbit crossing, and that's 3 times the size of that object in linear dimensions, so it's 30 times the mass. I would call these potentially catastrophic asteroids, not just potentially hazardous. I think that's hideous understatement. Now, WISE wasn't able to do a synoptic survey of the entire sky. Yes, Leonard?
Or when you say 30 or 150 meters, is this when they are through the atmosphere, or is how much do they lose through the atmosphere?
Almost, an object that's this size would lose almost nothing. Sorry. But of the objects that they did encounter in looking around the sky, they were able to project that to all of the near-Earth space and found an estimated 4,700 objects, each one of which could be life-ending on the Earth. And only 20 or 30% of those objects had actually ever been seen. Now, people being aware of this are starting to think of ways of deflecting these asteroids so they don't hit the Earth. This is a solar sail. This is using radiation pressure. This is a thing called a gravity tractor. Somebody ought to look at Newton's third law on that one. And this is a thing where they're actually nibbling away the asteroid using the material, but also making it smaller so that it's less hazardous. There's been no experimentation done on these. But I think what's interesting is, if you think about the idea of having to transport material from a mining operation, many of these technologies could be useful. So there's a synergy between mining and protecting the planet. Oh, and those little telescopes that I mentioned that Planetary Resources and Deep Space Industries are going to launch, those certainly have the potential to warn us of objects that have not yet been detected by the current network of sensors. And so there's another synergy between the mining operation and defending the planet. Of course, space mining, in another sense, could defend the planet. If we start bringing all of our electricity down from space, rather than burning coal and mining uranium on the Earth, we're defending the planet in another way. So hopefully I've at least addressed at a surface level some of these three issues. One is the interplay between the various phases of the mining mission, the exploration and the talent consumption. I hope that there's some appreciation of how important robotics are at all stages of this, and that technology sharing between servicing spacecraft in Earth orbit, asteroid mining, and planetary defense is both useful. We can kill several birds with one stone if we develop common technologies, but also that our planet may in fact depend on it. Thank you. Question? Guess it wasn't very soon. All right. Oh, good.
You briefly touched on the asteroid deflection. What, as a system, when you're looking at systems, which one do you think you would lean to?
Oh no. No, you're not going to trap me into that. I'm sorry. People that actually that understand space missions need to answer that question. I mean, some of them are attractive from the standpoint that, well, for example, the solar sail requires no propellant. But because the forces are so small, that the travel times are going to be very long, spiral orbits and that sort of thing. So again, there's this interesting trade-off of propellant versus time. I think that's going to wind up being one of the keys to the economics of mining. And I haven't any idea where the winning solution is. Was there another question?
Yes.
Hello. You haven't talked about an elevator. How
and I won't.
would that change? You won't. Okay.
Okay, no, all right. So if you have a situation where there's relatively low gravity, an asteroid or the moon and that sort of thing, an elevator sort of system may have some sort of applicability, even on the moon. I think if you look at trying to do elevators from the Earth where there's both a very deep gravity well and an atmosphere, certainly not in your grandchildren's lifetime will that ever come to pass. I mean, there are orders of magnitude missing in the strength of the fiber needed to do a space elevator from the Earth. But doing it in places where there's no atmosphere and much lower gravity wells, that may be something that's useful.
So like moon.
What? Yeah, I mean that's not an insignificant gravity well, but at least there's no atmosphere.
You mentioned that you were looking to optimize the process. Would you be able to elaborate on the algorithms that you use?
No.
Have you got any algorithms currently, or?
No.
Okay. Because
I'm being honest here. This is pretty new stuff.
Okay. Because I'm doing aircraft engineering, and there's a big part of it to do with multidisciplinary optimization. And so what they do is they look at the system, and there's various different parts, and they're all interacting, and each one affects the other. And so what they do is they plug that into a computer simulation, and they try and design an aircraft using a computational approach. And so there's this one company that's done some very good work here. I can't recall its name, but they managed to go through the preliminary design of a military aircraft, and that included up to 6 million design hurdles. So you could probably...
This artificial intelligence approach that I mentioned here is an alternative to multidisciplinary optimization. In the sense that if the knowledge base is complete for the domain that you're working in, that there are no ambiguities, that there is one provable optimum in the set of choices. Having said that, there's room for both. MDO is a great way to solve problems, and this can't handle the number of variables. Now we had 153 variables in our space design project that we were doing here, and it was able to find the optimal solution in 1 second for running. You know, but it's an exponential problem. So if you had 300 variables, it would be an hour and that sort of thing. So MDO, more variables, but also more ambiguity. You know, my observation is that if somebody was going to get serious about a system that's this complex, they would need to develop lots and lots and lots of decision support tools, of which MDO is a set, and this is another.
Also another thing, I noticed that you were looking at a way of grouping the asteroid physics in microgravity. And I came across a video, I'm not quite sure what the company was, but they were, instead of using, say, a 3-prong approach, where you've got 3 large points of contact, each prong has several kind of needle type.
I've seen that. Here's another way to do it. Don't give this away because I'm going to apply for a patent, but let's have a spacecraft flying along and it lowered a tether. As that tether encounters the asteroid, it will wind around it. And now you can pull yourself down to the surface and you have something to react against. The patent's on the mechanism, not on the company. I'm not really worried about that. So there are many ways to do it, but I've seen a harpoon concept to do this as well. I think that's relatively low probability of success.
Yeah, so we've got a lot of companies well, so far it's only really made planetary resources, deep-based industries, but a lot of plans to do things a lot of different ways. And things like we want to get maybe fuel from the moon to set up kind of infrastructure for them to get fuel while they're out there. Do you think there's a need for an international agency of some kind for these companies to work within to organize who's doing what, and instead of everybody trying to go out independently and do it themselves all the way?
So is there an international agency on Earth to coordinate coal mining?
No.
No, there isn't. And so the free market tends to work pretty well in my view. I'm not a communist, okay? I mean, it really does seem to do a great job of doing things efficiently. The question that the media frequently asks me is, well, what about regulations? I'm like, God, I hope we don't have any. I mean, the good news is that it is certain that there's no life on asteroids. Right? I mean, so we don't have to worry about ecology. Now there are other issues, but I think that there will be conflicts. I mean, if 2 people want the same asteroid, they'll have to have a duel or something. I don't know how. But